Here's a claim that sounds like science fiction. A computer that can search through 1,000,000 possibilities using roughly 1,000 steps instead of 1,000,000. No shortcuts, no cheating, no clever indexing trick, just a fundamentally different way of using the laws of physics. If that sounds impossible, you're not alone. Plenty of scientists thought so too, until they saw the math. Today, we're breaking down exactly how this works, why it's considered one of the most important breakthroughs in quantum computing, and where the real limits are hiding. Let's start with the machine itself, because none of this makes sense until you understand what a quantum computer actually is. A regular computer, the one in your pocket or on your desk, stores information as bits. Each bit is either a 0 or a 1, nothing in between, no ambiguity, just a clean binary switch that's either off or on. Every photo you've ever taken, every message you've ever sent, every video you've ever watched, all of it eventually breaks down into enormous strings of these simple zeros and ones, flipped billions of times per second by circuits smaller than a speck of dust. A quantum computer throws that clean simplicity out the window. Instead of bits, it uses qubits. And a qubit doesn't have to be strictly 0 or strictly 1. It can exist in something called a superposition, a strange in-between state where it's sort of 0 and sort of 1 at the same time, until the moment you actually measure it. Think of a coin spinning in the air. While it's spinning, it isn't heads or tails, it's something else entirely. A blur of both possibilities at once. Only when it lands, only when you observe it, does it collapse into one definite outcome. Qubits behave a little like that spinning coin, existing in a haze of possibility until measurement forces them to commit to an answer. Now here's where it gets even stranger. Qubits can also be entangled with each other, linked in a way that has no real analogy in the everyday world. When two qubits are entangled, the state of one is tied to the state of the other, no matter how far apart they are. Measure one, and you instantly know something about its partner. Einstein famously distrusted this, calling it spooky action at a distance, but decades of experiments have confirmed it's real. Superposition and entanglement together are the two ingredients that give quantum computers their strange power, letting them explore many possibilities simultaneously in a way that classical bits simply cannot. This is the part where people often expect me to say quantum computers are just faster classical computers, like upgrading from a slow processor to a fast one. That's not quite right, and it's an important distinction. A quantum computer isn't a better calculator. It's a different kind of tool altogether, one that's spectacularly good at certain very specific problems and completely unremarkable at others. For most everyday computing tasks, checking your email, browsing the web, editing a document, a classical computer is still the better choice, and will likely remain so for a very long time. Quantum computers earn their reputation in a narrow but powerful set of problems, and one of the clearest examples of that power is exactly the algorithm we opened with, the one that can search a 1,000,000-item haystack in roughly 1,000 steps. That algorithm is called Grover's algorithm, and it was discovered in 1996 by a computer scientist named Lov Grover, who was working at Bell Labs at the time. To understand why his discovery mattered so much, you first need to understand the problem he was solving, because it's a problem that shows up absolutely everywhere in computing, often in disguise. Imagine you have an enormous, completely unsorted list. Maybe it's a database of 1,000,000,000 records. Maybe it's every possible combination of a lock's tumblers. Maybe it's every conceivable password of a certain length. The list has no order to it, no alphabetical arrangement, no helpful index, nothing that lets you skip ahead or narrow things down intelligently. Somewhere buried in that list is the one item you're looking for, and your only tool is to check entries one at a time. On a classical computer, there's no clever shortcut here. You check the first item, it's wrong. You check the second, it's wrong, and you keep going. On average, you'll have to check about half the list before you find your answer. And in the worst case, you might have to check nearly all of it. If the list has 1,000,000 entries, you might need close to 1,000,000 checks. This is what computer scientists call an unstructured search problem, and it's considered one of the fundamental limits of classical computing. There simply isn't a faster general way to do it, no matter how clever your programming. Lov Grover asked a deceptively simple question. What if a quantum computer could search that same unsorted list dramatically faster, not by cheating, not by somehow knowing the answer in advance, but by exploiting the strange rules of quantum mechanics themselves? And astonishingly, the answer turned out to be yes. Grover's algorithm can find the correct item in a list of size n using roughly the square root of n steps instead of n steps. For a 1,000,000-item list, that's the difference between checking up to 1,000,000 entries and checking around 1,000. For a 1,000,000-item list, it's the difference between checking up to 1,000,000,000 entries and checking around 31,000. The bigger the list, the more dramatic the advantage becomes, and this quadratic relationship between the classical cost and the quantum cost is exactly what people mean when they describe Grover's algorithm as offering a quadratic speedup. Let's slow down and actually walk through how this works, because the mechanism is genuinely elegant. even if it takes a moment to wrap your head around. Grover's algorithm doesn't work by inspecting items one at a time the way a classical search does. Instead, it starts by putting all of the qubits representing the list into a superposition, so that in a very real sense, the quantum computer is examining every single item in the list simultaneously. Every possible answer exists at once, layered on top of each other, each with a certain probability amplitude attached to it. Now, if you tried to just measure the system at this point, you'd get a random answer, because every possibility currently has roughly equal weight. That's not useful on its own. What Grover figured out was a clever two-step process that can be repeated over and over, each time nudging the probability amplitude of the correct answer a little higher and the probability amplitude of every wrong answer a little lower, until the correct answer becomes overwhelmingly likely to appear when you finally do measure the system. The first step in that process uses something called an oracle. An oracle, in this context, isn't a mystical fortune teller. It's a mathematical black box that knows how to recognize the correct answer when it sees it, even if it doesn't know what that answer looks like in advance. Think of it like a lock that clicks open only when the exact right key touches it, without the lock itself understanding what makes that key special. The oracle flips the sign of the probability amplitude for the correct answer, marking it as special without revealing what it is to the observer. Everything else in the superposition stays untouched. The second step is called the diffusion operator, sometimes described as inversion about the mean. This step takes all those probability amplitudes, including the one that was just flipped, and reflects them around their average value. Because the correct answer's amplitude was flipped negative while everything else stayed positive, this reflection has a beautiful effect. The correct answer's amplitude grows, while the amplitudes of all the wrong answers shrink slightly. It's a bit like a group photo where everyone quietly steps back, except for one person who steps forward. And after a few repetitions of stepping back and stepping forward, that one person becomes unmistakably visible in the frame. You repeat this two-step cycle, the oracle marking and the diffusion amplifying, again and again. Each repetition rotates the overall quantum state a little closer toward the correct answer. And here's the elegant mathematical fact Grover discovered. You need to repeat this cycle roughly the square root of n times to maximize the probability of measuring the correct answer, where n is the size of your search space. Repeat it too few times, and you haven't amplified the correct answer enough. Repeat it too many times, and interestingly, you actually start to overshoot. The probability begins swinging back down again, which is a strange and counterintuitive feature of how these quantum rotations behave. Get the number of repetitions right, and when you finally measure the system, you'll pull out the correct answer with very high probability. This is genuinely different from how classical brute force search works, and it's worth pausing on why. A classical computer, checking a list one item at a time, gains information linearly. Each check either confirms an answer or rules one out and nothing more. Grover's algorithm instead builds up probability across the entire search space simultaneously, using interference between quantum states to reinforce the right answer while canceling out the wrong ones. It's less like checking boxes one by one and more like slowly tuning a radio dial until the static fades and one clear signal emerges. Now, it's worth mentioning something important here, something that researchers proved shortly after Grover published his work. Grover's algorithm isn't just a clever trick that happens to be fast. It's provably the best possible approach for this type of problem on a quantum computer. Researchers, including Charles Bennett, Ethan Bernstein, Gilles Broussard, and Umesh Vazirani, proved that no quantum algorithm can solve unstructured search faster than the square root of n, which means Grover's algorithm isn't just good, it's optimal. There's a hard mathematical wall here, and Grover happened to build an algorithm that runs right up against it. That's part of why this algorithm holds such a special place in quantum computing history. It's not an approximation of the best possible answer, it is the best possible answer. So why does any of this matter beyond academic curiosity? Because the concept of unstructured search, that seemingly simple problem of finding one needle in an enormous, disorganized haystack, shows up disguised inside an enormous number of real computational problems. Cracking certain types of cryptographic keys, for example, can be framed as a search problem, checking every possible key until you find the one that unlocks an encrypted message. Grover's algorithm, applied to something like a symmetric encryption key, could in theory cut the effective security of that key roughly in half, which is exactly why cybersecurity researchers have spent years thinking about what's sometimes called post-quantum cryptography, designing new encryption standards specifically to stay ahead of what quantum search might one day be capable of. Beyond cryptography, Grover-style search shows up as a building block inside all sorts of other quantum algorithms and applications. Puzzle-solving problems, constraint satisfaction problems, certain optimization tasks, database queries, and pattern matching problems can all sometimes be reframed as searches through a large space of possibilities for one that satisfies a particular condition. Because of that, Grover's algorithm isn't just a standalone party trick. It's become a kind of foundational subroutine, a tool that shows up embedded inside larger and more complex quantum algorithms, the way a basic sorting function might show up inside a much larger piece of classical software. Now, it's important to be honest about the limitations here too, because there's a lot of hype floating around quantum computing, and Grover's algorithm is often swept up in it. The quadratic speedup it offers is real and mathematically guaranteed, but quadratic is not the same as exponential. Some other quantum algorithms, most famously Shor's algorithm for factoring large numbers, offer an exponential speedup over the best-known classical approaches, which is a far more dramatic advantage. Grover's speedup, by comparison, is more modest. Going from 1,000,000 steps down to 1,000 is impressive, but it's not the same as going from 1,000,000 steps down to 20. And there's a practical catch that researchers at IBM and elsewhere have been careful to point out. Classical computers today run at staggering speeds, executing billions of operations every single second on hardware that's been refined and optimized for decades. Quantum computers, by contrast, are still in a relatively early and fragile stage of development. Qubits are notoriously delicate, prone to losing their quantum properties through a process called decoherence, and prone to errors from even tiny amounts of environmental noise, stray vibrations, temperature fluctuations, or electromagnetic interference. Building a quantum computer with enough stable, low-error qubits to actually outperform a classical computer on a real-world unstructured search problem, once you account for all the engineering overhead, remains a serious unsolved challenge. In other words, on paper, the quadratic advantage is undeniable, but translating that paper advantage into a real, practical, everyday advantage over classical hardware is a very different and much harder problem, one that hasn't fully been solved yet. That said, researchers have made genuinely exciting progress recently, and it's worth walking through some of what's actually happening in labs right now, because it shows the field moving from pure theory toward real experimental validation. Scientists working with quantum processors from companies like IQM have been running Grover's algorithm on chips with 9 and 16 qubits, using it as a kind of stress test or benchmark to measure how well different generations of hardware perform. What's fascinating is that these tests have revealed something counterintuitive: newer hardware isn't automatically better. Careful calibration, precise control over each qubit, and thoughtful error characterization sometimes matter just as much as raw upgrades to the chip itself. That's a humbling but important lesson for an industry that sometimes gets caught up in simply chasing bigger qubit counts. Elsewhere, physicists at the University of Innsbruck have pushed things in a different direction entirely, focusing not on raw speed, but on reliability. Using a trapped ion quantum processor, they successfully ran a fault-tolerant version of Grover's algorithm across 3 logical qubits, built out of 8 physical qubits working together, without needing what's called mid-circuit measurement, a technique that normally requires pausing the computation partway through to check on its progress and correct errors. Running the algorithm without that interruption, and still getting the correct results, is a meaningful step toward more stable, more reliable quantum computation, since interruptions and corrections of that kind tend to introduce their own risks and slowdowns. Other researchers have been exploring how far the underlying concept of Grover's algorithm can stretch beyond simple qubits altogether. Some teams have been experimenting with what are called qubits, multi-level quantum systems that can represent more than just 2 states the way a standard qubit does, and they've shown that Grover-style search can be extended to work efficiently on these more complex systems, while still preserving that same elegant square root scaling. Other researchers have even found surprising links between Grover's algorithm and completely different fields of physics, drawing connections between the mathematical structure of Grover's search and techniques used in quantum imaging and optics, suggesting that the underlying ideas behind this algorithm might have applications far beyond what anyone originally imagined back in 1996. At the same time, some recent studies have poured a bit of cold water on overly optimistic expectations, and it's worth including that perspective too, because a balanced picture matters more than a purely enthusiastic one. Researchers testing Grover's algorithm on realistic text and string search tasks using simulated quantum hardware found that while it performs beautifully on small, clean, exact match problems, it runs into real trouble when applied to larger, messier, more semantically rich data, the kind of data you'd find in real-world search engines or databases. Designing the oracle, that black box responsible for recognizing a correct answer, becomes dramatically more complicated and resource-intensive as the data gets more complex, and the qubit requirements needed to represent that data can balloon out of control. In some cases, attempts to parallelize the algorithm for these harder problems ended up behaving more like brute force classical search than a genuine quantum speedup. Findings like this are a useful reminder that Grover's algorithm shines brightest in clean, well-defined search spaces, and that applying it to messy, real-world data is still very much an open area of active research. On the more applied and creative side, other researchers have used Grover's algorithm as a tool for tackling notoriously difficult puzzle-style problems, the kind mathematicians call NP hard, things like cryptarithmetic puzzles, jigsaw-style constraint puzzles, Boolean satisfiability problems, and logic-based number puzzles. By combining Grover's quantum search with classical pre-processing and post-processing techniques in a hybrid approach, some teams have managed to simplify the Oracle design process itself, reducing the number of quantum gates needed and successfully solving real puzzle instances using simulated, noisy quantum hardware. It's a nice example of how theoretical algorithms slowly get adapted, reshaped, and combined with classical techniques as researchers try to find the sweet spot where quantum advantages actually translate into practical results. There's another angle worth exploring here because people often ask a very reasonable question. If Grover's algorithm is so well understood and mathematically proven, why hasn't it already changed the world the way some headlines seem to promise? Part of the answer lies in something researchers call the crossover point, the theoretical size. A search problem needs to reach before a quantum computer running Grover's algorithm would actually beat a classical computer running brute force search, once you account for every bit of overhead involved in building and operating real quantum hardware. That crossover point turns out to be enormous, likely requiring search spaces so large and quantum hardware so clean and error-free that we simply haven't gotten there yet. It's a bit like owning the blueprint for a supersonic jet decades before anyone has built an engine capable of actually reaching supersonic speeds. The design is sound, the physics checks out, but the engineering has to catch up before the promise becomes reality. This is also why so much current research focuses less on chasing dramatic real-world speed records and more on refining the basics, reducing error rates, extending how long a qubit can hold its quantum state before decoherence sets in, and finding smarter ways to correct mistakes as they happen rather than after the fact. Error correction in particular has become one of the central challenges of the entire field. A single physical qubit today is still fairly unreliable, prone to flipping unexpectedly due to the smallest disturbance from its environment. To get around this, researchers often bundle many physical qubits together into what's called a logical qubit, a kind of redundancy system where errors in individual physical qubits can be detected and corrected without disturbing the overall computation, much like how a single corrupted letter in a word can often still be understood correctly if enough surrounding context survives. Building enough clean logical qubits to run something as robust as Grover's algorithm at a genuinely useful scale is widely considered one of the biggest remaining engineering hurdles in the entire field. And it's a hurdle that companies, universities, and government-funded labs around the world are racing to clear. It's also worth pointing out that progress in this field rarely arrives as one single dramatic breakthrough. Instead, it tends to show up as a steady accumulation of smaller, less flashy improvements. A slightly longer coherence time here, a slightly more accurate gate operation there, a clever new way to encode information that shaves off a bit of overhead. Individually, none of these improvements sound particularly exciting, but stacked together over years, they're exactly the kind of incremental progress that eventually turns a theoretical curiosity into a practical tool. Grover's algorithm has essentially been waiting, patiently mathematically unchanged since 1996, for the hardware around it to finally catch up to what the math has promised all along. Stepping back from all these individual experiments, there's a broader story here worth appreciating. Grover's algorithm has become something like a universal benchmark in the quantum computing world, a relatively simple, well-understood algorithm that researchers can implement on almost any type of quantum hardware, whether that's superconducting circuits, trapped ions, or photonic systems, to test and compare how well that hardware actually performs. It's simple enough to implement without years of specialized engineering, yet demanding enough to genuinely stress test a quantum processor's qubits, its gates, and its error rates. In that sense, Grover's algorithm plays a role in quantum computing a little like a standardized test plays in evaluating students, not because it's the ultimate goal in itself, but because it's a consistent, well-understood way to measure progress across an entire, rapidly evolving field. It's also worth remembering just how significant it was, historically, that this algorithm emerged at all. In the mid-1990s, quantum computing was still largely theoretical, an intriguing area of physics with almost no experimental hardware to speak of. Just a couple of years before Grover's discovery, Peter Shor had already stunned the computing world by showing that a quantum computer could factor large numbers exponentially faster than any known classical algorithm, a result with enormous implications for cryptography, since much of modern encryption relies on the extreme difficulty of factoring large numbers. Shor's result proved that quantum computers weren't just a theoretical curiosity. They had the potential to fundamentally reshape entire fields. Grover's algorithm, arriving shortly afterward, offered something different but equally important: proof that quantum speedups weren't limited to one narrow, specialized mathematical problem like factoring. Instead, a quantum computer could offer meaningful advantages for one of the most general, most fundamental problems in all of computer science: the simple act of searching. Together, Shor's algorithm and Grover's algorithm became the two pillars that every introductory quantum computing course still builds around today. One demonstrating a dramatic exponential advantage for a specific problem, and the other demonstrating a provably optimal, broadly applicable advantage for an almost universal problem. So where does all of this leave us today, 3 decades after Lov Grover first published his idea? The honest answer is that we're still in the middle of the story. The mathematics behind Grover's algorithm isn't in question. It's been proven correct and proven optimal, tested repeatedly on real quantum hardware with results that match theoretical predictions. What remains uncertain is the engineering side of the equation: building quantum computers with enough qubits, low enough error rates, and long enough coherence times to actually run Grover's algorithm at a scale where it meaningfully outperforms classical computers on real practical problems, not just small demonstrations in a research lab. Every year brings incremental progress, better qubit designs, smarter error correction techniques, more clever ways of extracting useful results out of noisy, imperfect hardware, but the finish line, genuine practical quantum advantage for search-based problems in the real world, still lies somewhere ahead of us. What makes Grover's algorithm such a compelling story, though, isn't just its technical elegance, it's what it represents about the nature of scientific progress itself. It's a reminder that some of the deepest, most disruptive breakthroughs come not from building bigger or faster versions of what already exists, but from asking a fundamentally different kind of question. Lov Grover didn't try to build a faster classical search algorithm. He asked whether the very rules of physics governing our universe might allow for a completely different way of searching altogether, and it turned out they did. Superposition let a quantum computer consider every possibility at once. Interference let it amplify the right answer while quietly canceling out the wrong ones. And decades of careful mathematical proof confirmed that this wasn't just a clever trick. It was the best possible answer physics allows. That's really the heart of why this algorithm still matters today, and why researchers across the world, from university labs in Latvia to trapped ion experiments in Innsbruck to superconducting processors built by major technology companies, keep coming back to it again and again. It's simple enough to teach, elegant enough to inspire, and powerful enough to remain, decades after its discovery, one of the clearest windows we have into what quantum computers might one day be capable of, if we can just build the hardware sturdy enough to carry that promise all the way through. And as qubit counts grow, as error correction techniques mature, and as researchers keep pushing the boundaries of what today's fragile quantum processors can reliably do, that square root speedup Lov Grover discovered back in 1996 might finally start moving from an elegant mathematical curiosity to something the real world can genuinely feel.